One method that mathematicians and calculus students like to use to approximate the definite integral is called the Riemann Sum method. Now, the Riemann Sum method pretty much is just using rectangles to approximate the definite integral. For instance, in our example here, we have a natural log function. If we were to find the definite integral from x equals 2 to x equals 6, what we could do is divide the area underneath this curve into a bunch of rectangles. So I'm going to randomly draw some rectangles that kind of look like they cover the area underneath this lovely function. So now we have 5 different rectangles, or sometimes we call each of these rectangles increments or subintervals. Now the location where each of these rectangles intersects the function corresponds to a different x value, which will be called C1, C2, C3, etc., or sample points. So over here we would have a C2, and over here we would have a C3, etc. So our goal in the definite integral is to find the area underneath this curve. So how would we use our rectangles to approximate this area? Well, pretty much what we're doing is taking a sum of the area of each of these rectangles. So one way we could write this is by starting with k equals 1, and k will correspond to each of these increments, and we will have a change in x, delta x, corresponding to 1, 2, 3, 4, 5, all the way until we have our n number of increments, which in this case is 5, and we're going to multiply by the height of each of these rectangles. Now the height, we're going to call this the function value at ck. So if we wanted to find the area of this rectangle, we would be multiplying the delta x for this corresponding k value, the second k value, and multiplying it by the height of the rectangle, which is the function value at this point, C2.